Jai Shri Krishna. Greeting to one and all. It gives me immense warmth and great pleasure to grace all of your presence in the interest of today's webinar on Graceful Tree Conjecture, organized by PG and Research Department of Mathematics, DG Vaishnava College. So before we begin today's webinar, I would like to express my heartfelt gratitude to all of you who sincerely committed to this event to make it as a success. Now, I invite Dr. B. Abhirami, Organizing Secretary, Assistant Professor, PG and Research, Department of Mathematics, to welcome the gathering, which is followed by Tamil Thai Valthu and our college prayer. Ma'am, over to you, ma'am. Abhirami, ma'am. Abhirami, ma'am.
Yes. Good morning to all. It is a moment of great privilege and honor for me to extend a warm welcome to all of you present here on behalf of Postgraduate and Research Department of Mathematics, DG Vaishnava College, to today's national webinar on Graceful Tree Conjecture. One of the most famous open problems in graph theory is the graceful tree conjecture, which states that every finite tree has a graceful labeling. This graph labeling finds a broad range of applications: the study of neofields, topological graph theory, coding theory, radio channel assignment, communication network addressing, and database management. A hearty welcome our Honorable Resource Person Dr. G. Seduraman, Professor, Department of Mathematics, CEG Campus, Anna University, Chennai. I am sure that this webinar would be great exposure for all the participants present in this webinar.
எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் மிகுந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
சத்யவ்ரதம் சத்யபரம் த்ரிசத்யம் சத்யஸ்ய யோனிம் நிஹிதம் ச சத்யே சத்யஸ்ய சத்யம் ருதசத்யநேத்ரம் சத்யாத்மகம் த்வாம் சரணம் பிரபன்னாஹ. वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिः सतां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनामविभेदेन जगत्क्रीडति यो यतः. ॐ शान्ति शान्ति शान्तिः.
Webinars are organized and conducted for the audience, the participants, research scholars, academicians to gain insight and information that would remain effective in their life, exercise, and work. Now, I invite Dr. S. Hariharan, Assistant Professor, Department of Mathematics, DG Vaishnu, to welcome our today's expert. Hariharan, sir.
Very good morning to one and all. I am very much delighted to introduce Dr. G. Sethuraman, Professor, College of Engineering, Guindy, Anna University. Sir has completed his master's and undergraduate from Madurai Kamaraj University, and completed his MPhil from Loyola College, Chennai. And Sir has his doctorate degree from University of Bombay. And after that, he completed his postgraduate research in graph theory from Faculty of Science, Indian Institute of Science, Bangalore, during the period 1992 and 1994 on coloring problem. And after that, Sir also completed a second postdoctoral in graph theory from Faculty of Science, Goldsmith College, University of London, on Erdos-Faber-Lowas conjecture. Dr. Sethuraman's specialization is on graph theory, theoretical computer science, and he is also a member of the professional organization Forum for Interdisciplinary Mathematics, FIM USA. Sir has guided 6 PhD scholars and currently guiding 7 research scholars. And also, he completed ME, MTech projects of 27 students. To his credit, he has more than 50 international publications. And to talk about the awards and honors, Sir has NPHM Postdoctoral Fellow given by National Board for Higher Mathematics from DAE, Government of India, and also Commonwealth Scholarship given by Commonwealth Scholarship Commission from United Kingdom. Sir also published one book on graph theory and its application. He worked as a postdoctoral fellow in University of London during the period 2001. And also he is a visiting associate professor in University Technology Petronas, Malaysia. And with this brief introduction, as well as with the vast experience in graph theory, sir, I would like to invite you and take the podium to give a lecture on graceful tree conjecture. We are welcoming you, sir. Please, the stage is on yours.
Yeah, thank you. Thank you very much. Can you hear me?
Yes, sir.
Right. Okay. Thank you very much for the introduction. I'm very much delighted to share my work. Now I'll present my talk.
Sir, your presentation, can you share once again? I think that. Yes, sir.
Share பண்ணுங்க.
Yes, sir.
I'm going to talk about one of the popular conjectures in graph theory called graceful tree conjecture. This was posed in the year 1967, over 50 years. This problem withstood and it is unsettled. It shows that the complexity of this problem. Slowly we get into that problem. Let me introduce the labeling as a game for the convenience of students. Now we are going to define a number game on graphs. A number game on a graph G with M edges is simply an assignment of distinct numbers from the set 0, 1, 2, 3, M to the vertices, such that for every edge UV, we simply measure or define edge label by understanding the difference of the end labels and take the absolute value of that. So it is a simple game. What we have to do is For a given graph, understand the number of edges. Then we have to, suppose m is the number of edges, then we have to assign distinct numbers to the vertices using the numbers 0, 1, 2, 3. Yeah. That is always possible because the number of edges is always either equal. I mean, the number 0 to m is at least equal to number of vertices or more than that. So what is in addition to that we have to do is simply for every edge, we understand or define the edge label. What is the edge label? Find the difference of the end labels of the edge and take the absolute value. That is the game. This game is always possible for every graph. So once it is possible, then we have to pose some kind of constraint. What is the constraint we are going to pose is this. A game, the number game, a number game on a graph G is called successful or graceful if all the edges of G get distinct labels from 1 to m. So playing a number game on G is always possible. When it's possible, we introduce constraint to make it more interesting, and therefore we define the game to be successful or graceful if all the edges of G gets a distinct numbers from 1 to m. That is a constraint. Suppose a graph admits such a successful number game or numbering scheme or graceful number scheme, then we call that graph is graceful graph. Okay. Let's look at an example. For example, if you take a path on 7 vertices P7, we ask the question whether it is graceful. For that, what is that we have to do? We have to understand the number of edges. Here, 6 edges. Therefore, we have to assign the number from 0 to 6, distinct number to the vertices. Here it is just enough because 7 vertices are there. Numbers are 7, therefore it is just enough. And we have to assign the distinct numbers to the vertices. So that is not really difficult. We can assign like this. So I have done some kind of assignment. I don't have any in mind. Just like that, I want to assign simply distinct numbers. That's it. Right. After assigning, I want to understand what is the edge label. The edge label is find the difference and take the find the difference of the end labels and take the absolute value. For every edge, find the difference of the end labels and take the absolute value. So therefore, the edge label of this edge is 6. Edge label of this edge is 4. Edge label of this edge is 3. Edge label of this edge is 4. Edge label of this edge is 3. Edge label of this edge is 1. Now we see that by our assignment this way, we are not getting distinct label to the edges. Therefore, our assignment, our game is not successful. Therefore, we have to change the strategy. Let us change the strategy. What is the strategy now we are doing is, we are going in a methodical way. What is a methodical way? For the origin, we assign 0. For the next vertex, its neighbor, we assign the largest available label, that is 6.
Sir, excuse me, sir.
Yes.
Hello, sir.
Can
you make it full screen, sir?
Yeah, I will do that. Yes.
Yes, sir. That will be nice. Yeah.
Yes.
Thank you, sir. Yeah. Now it's very clear. Thank you so much.
Right. Okay. Thank you. Right. Yeah. Please interact if you have any inconvenient or ask the question also, please. Yeah. So next vertex, we assign the what is the available largest value. For the next vertex, we are assigned the next available least value. So that is 1. For the next vertex, we use the next available largest value. That is 5. Next vertex, we assign the least value. So what is the next vertex? We are assigned the available largest value. And next vertex, available least value. That is a strategy we have adopted. Earlier, I have not adopted any strategy. Randomly, I have assigned distinct numbers. But here, I am consciously doing the assignment. That is a strategy I am following for gaming my game to be successful. So then I look at the edge label. The edge labels we are getting as distinct. Therefore, the strategy which adopted is successful. Therefore, this game is successful game, or in other words, it's a graceful game. Therefore, the graph, since the graph admits graceful game, therefore we say that the graph is graceful, the path is graceful now. Okay, so it is not necessary that our strategy is unique. It can be many also. Once we have strategy, we can try to find another strategy also. For example, this is another strategy of the path, same path. We can get the distinct labels. We assign the distinct labels to the vertices. That in turn induce distinct label to the edges as well. So therefore, it is possible to have many successful strategy, graceful labeling. So for the path, it is possible to define many successful graceful labeling or graceful numbering. So it is possible. Therefore, path are graceful. In fact, this can be generalized to any path. Okay, this is strategy we can follow and we can generalize to any path. Next, what we do, we want to understand this strategy of a little more constrained graph-wise. We pose it. We take a more constrained graph and try to challenge the player. Therefore, we give this little more constrained graph. So this is the caterpillar. What is caterpillar? If you remove all the boundary vertices, we get a path. We know the strategy of path. Therefore, we give the next challenging structure that's called caterpillar. So is it possible to say that caterpillar is graceful? So we know what is the strategy, the path strategy. Try to imitate that in this also. There we are trying to imitating that. So this vertex I have given 0, the least label. For the neighbors, I'm using the available largest values. Therefore, 21, 20, 19, 18, 17, 16. For the neighbor of 16, I use the least available labels, that is 1, 2, 3, 4, 5, 6. For the neighbor of 6, I use the available largest values, 15, 14, 13, 12, 11, 10. And 10, we use the available least labels, 6, 7, 8, 9. Therefore, it is, we have completed the assignment of vertices. Whether it will give the desired edge label, let's look at that. So in fact, it is also giving beautifully the distinct edge labels. Therefore, the caterpillar also graceful. It's nice to see that. So therefore it increased the curiosity that we can explore many graphs to be graceful. So next we ask the question: are the cycles graceful? Let's look at the cycle C7. We try to give the assignment distinct value to the vertices. So we have assigned the distinct numbers to the vertices from 0 to 7, and that it is somewhat modified strategy of path, and we can see that 0, 7, 1, 6. But here there is a one skip because we have one well must be skipped for the cyclist concern. Therefore, we again 3, 5, 4. So this, let's see that the induce the distinct edge label. Indeed, it induces a distinct edge label. Therefore, this graph is graceful. So we have got successful scheme. Okay. Now let's look at the next cycle, C8. Again, we can do that. Same strategy we can apply, and then we can get it. So, however, we cannot believe that every cycle can be graceful. It is very interesting to note that these two cycles are not graceful. However, you try to do that, it is not possible. So what is interesting thing about that same cycle structure, but with different parity of the vertices, the strategy fails. We cannot do that at all. So that makes more interesting because it is challenging to understand the structure and parity and many more things, the intricacy in this structure. Therefore, understanding graceful graph becomes interesting too. So next we go to the complete graphs. It is evident that K2, the complete graph K2 is graceful, and K3 also graceful. Easily one can get it. K4 is graceful too, and strategy is slightly modified. It is not path strategy. We have to adopt a different kind of strategy because the number of edges more. Therefore, we have to be very cautious about that strategy. Then, surprisingly, if you look at K5, it is not possible to define any strategy to make the graph to be graceful. Always we get the repetition of edge labor. It's really challenging. So this makes more interesting. Not all the complete graphs are graceful. So therefore, now let's look at the complete bipartite graph. So this K23 is very nicely satisfying the gracefulness. So bipartite graph, we can adopt easy strategy. What is that strategy? Is that for the upper part vertices, we can give the continuous numbers 0, 1, 2, 3, etc. For the lower part, we can just give the multiple of m. This is m, this is n. Then we can give the multiple of m. Therefore, 2, 4, 6. This works to be graceful. And in fact, this can be generalized. In fact, all complete bipartite graphs are graceful. And Peterson graph seems to be notorious in many cases, but it is beautifully satisfying the gracefulness. So we are able to give the graceful scheme. And indeed, Peterson graphs are graceful. And there are non-graceful graphs and 5 vertices. In fact, these three are the non-graceful graphs and 5 vertices. So it is really making more interesting, because there are graphs which are graceful and there are graphs which are not graceful. So therefore, it makes us to understand in detailed way what are the graceful graphs. So far, we have seen some examples. For example, cycles are graceful if and only if the cardinality n is the number of vertices. N must be either in this form of congruent to 0 or 3 mod 4. Complete graphs are graceful if and only if n is less than or equal to 4. All the complete bipartite graphs are graceful, whatever the value of m and n. And all the wheels are graceful. Peterson graph also graceful, and so on. There are this list goes on. However, understanding the structural property of graceful graph is going to be amazingly challenging for us. This is one of the hardest ever problem existing in the graph theory. It's a very, very difficult problem in graph theory. Okay. So next question is, at least, can we say at least trees are graceful? Are we good enough to say this one? Is it possible to say, is every tree graceful? Of course, it is not. Still, this question is not answered. Only conjecture is made. In 1967, Rosa, Godzik, and Ringel, they have conjectured that all trees are graceful. Still, this conjecture is open, unsettled. More than 50 years, it is challenging, right? And we are not able to find appropriate tool, appropriate strategy for all trees. So that is a really challenging one. So then we want to understand, how do you approach this conjecture, and how to settle this conjecture? Is there any kind of things hopefully we can some point of time we can reach, or can we have any basic understanding, or structural understanding can we make, or are the results available? So let's look at this now. If you take any tree with at most 27 vertices, there is an algorithm proposed by Alred and Mackay. They have kind of not really very good algorithm, but it is an algorithm which modifies the labels whenever the repetition comes, and then it try to give that graceful labeling. It works up to 27 vertices. Beyond that, the algorithm fails. And that strategy is further developed by Michael Gordon in his MS thesis, and he has shown that any tree with at most 27 vertices are graceful. And there is a heavy project going on for the verification project, graceful tree verification project going on in China, and Professor Fang has verified all trees with at most 35 vertices are graceful. Yeah, this is status of the largest size of trees known to be graceful. If you look at the families of trees, we have seen that all paths are graceful. The strategy we have seen. The caterpillars also, we have seen the strategy. All caterpillars are also graceful. This was proved by Rosa himself on his first paper, ever first paper written on the graceful labeling. Rosa's paper, it's a classic paper. It's a classic paper. In that classic paper itself, he gives that interesting result. This we have seen, right? It's very surprisingly lobsters. What is lobster? Lobster is a tree. If you remove all the woody vertices, we get a caterpillar. We have seen caterpillar is a tree. If you remove all the woody vertices, path. Paths are graceful. Caterpillars are graceful. If you take the lobster, if you remove all the woody vertices of the lobster, we get caterpillar. However, the lobster strategy of the lobster is not known till today. This is sub-conjecture. Berman proposed in 1979. All lobsters are graceful. Still, it is not proved so far. That is the complexity of this problem. This tree is looking very simple, but we are not able to come out with a perfect strategy for all lobster having to have graceful numbering scheme. That is the challenge of this conjecture. Probably audience now you can understand what kind of challenge it poses, why this problem withstood over half a century. Right. Now if you look at this, but however, there are specialized lobsters are proved to be graceful. For example, lobster with perfect matching are shown to be graceful. There is a very simple structure called family of spider, what is called olive tree, that is defined to be taking k paths. The first path is having length 1, second path is having length 2, third path is having length 3, and the eighth path is having length I, and so on, and merge all the origin of the paths together. Then that structure is called the olive tree. This olive tree is graceful. The strategy is developed for this olive tree. However, if we make little more generalization on this, that's called generalized olive tree. That is defined to be take any k paths randomly and merge the origin together, all the origins together. Then what the structure you get is the olive tree. This olive tree, generalized olive tree, still it is not proved to be graceful. So you can see that how the complexity increases. One strategy, knowing one strategy, we are not able to apply for the generalization of the same structure. For example, the caterpillar generalization, the leg growth generalization wise, lobster is obtained, but the strategy fails there in the lobster. This olive tree, there is a strategy for giving graceful labeling for olive tree, but we generalize, that strategy fails there. So that's why the conjecture is difficult, because every tree, class of tree, we need a separate strategy. So knowing one strategy, we cannot simply extend to other generalization. So that makes the problem to be more challenging. Symmetric tree is a tree, a rooted tree, in which every level vertices have the same or equal degree. That is the symmetric tree. This is proved to be graceful. Right? Berman himself proved in the classic paper 1976. It's all symmetric trees are graceful. It is one of the interesting results. Okay. Then banana tree is defined to be a tree with diameter 6, which is defined like this. Take any number of star 1, star 2, star 3, star 4, star 5, and take one of the leaves, identify one of the leaves, of this second star, identify one of the leaves of second star, third star, fourth star, and so on, and take one more new vertex and join the identified leaves, all the leaves with this one new vertex. This is called banana tree. The tree thus obtained is called the banana tree. This was sub-conjecture in the 1997. that all banana trees are graceful. Then, the 2009, my student Jabal Jacinta proved that these all banana trees are graceful. So it's like that. We identify some subclass of this. Even that strategy, it takes a longer time to establish. One of the fine result proved in the literature survey of graceful tree is that all trees with the diameter at most 5 are graceful. This is a very nice result in the graceful tree uh, conjecture. And here the Crenshaw and the Javier, they have proposed a new technique called transfer technique. The transfer technique is very interesting one that starts with one graceful tree and modifies the structure with the label and modifies and modifies, and the modified structure finally become graceful. That is a very interesting technique proposed by Crenshaw and Javier. It appeared in 2001. Okay. That technique, in fact, we have used here to prove that. That's why we, even this sub problem, waited for this technique. The technique earlier it was not known. That's why it took some time. There is another interesting tree known to be graceful tree is binomial tree, which is defined recursively. Binomial tree with order 1, that is one vertex is 0 edge, one vertex is single vertex. Binomial tree with order 1, that is one edge is one single edge. Binomial tree with the B to order 2 is the taking 2 copies of B1, and this is the root of the B1, taking 2 copies. This is B1 and this is B1. Join the root of the left subtree with the right subtree. So B3 is defined, take 2 copies of B2, this is B2, another copy of B2, and join the root of the left subtree with the root of the right subtree. And this becomes the root of the combined tree. So that's how it is defined recursively. So B0 is single node, and in general, the binomial tree of order k is defined from 2 copies of binomial tree of order k minus 1, and take the root of the left subtree, join that with the root of the right subtree. The root of the right subtree becomes the root of bk. That's how it is, right? Okay, so it is defined to be a binomial tree. This tree is used as a good data structure, or nice data structure in computer science, and this is a well-established tree. And this tree is shown to be graceful in the recently by 2020 with my student Raul Kumar. And so this is how we explore the graceful trees, with the different structures, specialized structures. We keep on defining and keep on giving a specialized strategy. Then how we solve the graceful tree conjecture? What is the way to approach and solve the graceful tree conjecture in general? Is there a way to approach? So definitely it's very difficult to, right now, at this moment, it looks very difficult to set the conjecture. At least we have to see that learn to handle the arbitrary tree in some form, and negotiate the graceful tree strategy. So what we have done is we have taken an arbitrary tree, but we are not able to give a graceful tree scheme, numbering scheme. Graceful labeling number scheme for that arbitrary tree. But however, what we have done is we are able to find the super tree containing the given arbitrary tree. For that super tree, we are able to give a graceful number. That we have done. That is, we are able to come out with embedding any tree in a graceful tree. So we have developed a technique by which we can embed any tree in a graceful tree. Or in other words, we can say every tree is a subtree of a graceful tree. So there exists a graceful tree containing a given tree as its subtree. That is the strategy we have proposed. And also we have given a strategy how this our method, the algorithm, or our construction can help to solve the graceful tree conjecture if some further problem is solved. That is the method we have proposed. That one I'm going to illustrate through an example. So that idea I'm going to propose with the example, or in other words, I'm going to illustrate our idea. So what is our idea is, I start with arbitrary tree. Eventually, I construct a super graceful tree containing given tree as its subtree. That is the idea. So you are given with arbitrary tree. Hope you are following, right? Am I going very fast, or is it okay? This audience, are you able to follow? Right, right. Okay. So I'm input is arbitrary. The input arbitrary we have taken as 16, having 16 edges. So I understand the longest path. This is the longest path. I take the origin of the longest path as the root. And all the vertices of the longest path appear as the leftmost vertex in each level. Then I'm going to assign labels to the vertices, level wise. First, I assign the labels to the even level vertices. Then I'll come to assign the labels to the odd level vertices. So for the even level, I just give the start from the root, the 0 level, we give the 0. Then second level, we give the vertices label from left to right. Least available labels, 1, 2, 3. Then we go to the next even level and assign the least available label one by one, 4, 5, 6. Then you go to the next even level and assign the label from least available label from left to right, 7, 8, 9, 10. Okay, then we are going to assign label to the odd level vertices from the bottom. We have assigned the labels to the even level vertices from the top to bottom. Now we are going to assign the label to the odd level vertices from bottom to top. Now, so and for the odd level vertices, we assign the labels from right to left. All right. So this odd level vertex, we assign the label as 11, the next label itself. For this one, we assign 11 plus 7. The 7 is defined to be the strength of this level. What is the strength of the neighborhood strength? That's called neighborhood strength of this level, odd level. What is the neighborhood strength? Number of vertices in previous level plus number of vertices in the next level. That is 7. Therefore, 7 is added to that. Again, 7 is added to 18, 25. Then we go up and we are going to assign label to this. For that, we understand what is the neighborhood strength of this level. That is number of vertices in the previous and the next. That is 6. Therefore, 25 plus 6, 31 we are going to assign. Then for this vertex going to the left side, we say assign 37. That is 31 plus 6, 37. And we have assigned, again, same strategy we apply to the assign the first level vertex. Understand the neighborhood strength of this first level, that is 4, 37 plus 4, 41 we assign. So we have assigned the distinct numbers. Actually, to Graceful, we have to assign the distinct numbers from 0 to 60, but we have gone up to 41. So actually, we have not given Graceful label to this given tree, but we have range extended beyond 16 and we got up to the 41. Let's look at the edge label. If we look at the edge label, we are getting here is 1, 9, 17, 18, 6, 14, 21, etc. All the labels are distinct. Why it is distinct? the edge label pattern goes like this: 1, 6, 9, 14, 17, 18, 21, 25, 30, 32, 33, 36, 38, 39, 40, 41. This, it forms a nice monotonically increasing sequence. We can arrange the edge labels as a monotonically increased sequence. Therefore, edge labels are distinct. So we got beautifully the distinct labels to the vertices and distinct label to the edges. However, we have gone beyond the range what should be. That is, the range is up to 16, but we have gone up to 41. So that is a negative point of our strategy. But this negative point, we are going to compensate with growing the tree to have 41 edges. So I'm going to identify a super tree which will have 41 edges, 42 vertices. That is our idea. That will have all the missing vertex labels and edge labels. So the strategy is like this. So right now we are given tree T is labeled with, and it is denoted as T prime. That is this tree. T prime is the given input tree with a label, with increased range of label. Now we are going to grow a super tree T star, which will have the vertices, 42 vertices that will have a label from 0 to 41. That will have 41 edges, that will have edge label from 1 to 41. Once we do like that, then the T star will be a graceful. That is our idea. How to do that? That is what we are going to do. Propose an algorithm for that. The algorithm, first step is we identify the X, the universal labeling set. That is what all label set, 0 to 41. And the second is we identified the existing vertex label set, V out. All the vertex labels here, existing vertex labels are here. And we remove 0 from the V out, that is V naught. And all the existing edge labels, it's called E out, right? And there are common label between V naught and E of T. We identify I. And what we do is we remove the common label from V naught, that is V star. And we remove all the common label from E of T, that is E star. This is the V star. V star meaning that this is only the vertex label, appearing as the vertex label. And E star is only appearing as the edge label. That is the quality of V star and E star. Quality of V star and E star. Okay, so what is that we are going to do? The one basic understanding of graceful tree is tree has V vertices, the number of vertices is M, then the number of edges M minus 1. Or in other words, suppose the tree has M edges, the number of vertices will be M plus 1. So, therefore, the available label will be M plus 1 exactly. Therefore, all the label from 0 to 41 should be used as vertex labels. And 1 to M or 1 to 41 should be realized as the edge label. So, therefore, every label except 0 should appear as both vertex label and edge label. And 0 should appear as only vertex label. That is the basic principle of graceful tree. Right. Okay. Now we have seen here what is that is this. V star is exclusively vertex labels. E star is exclusively edge label. Okay. Now we go to the, and obviously this as a tree, because 0 is removed, this V star, number of vertices in V star and number of edges in E star is equal. And now we are going to identify X star, which is removing from the X, removing all the existing label as a vertex label or as an edge label. Simply remove it. Right? Simply we remove all the existing label, either as a vertex label or as the edge label. We simply remove it. This is X star. Is that X star is These labels neither appearing as the vertex label or as the edge label. There's a basic principle of the graceful tree is every label should appear as a vertex label as well as the edge label except 0. So therefore, these labels, if you want to have graceful tree with 42 vertices and 41 edges, these labels, all these must in that tree must appear as both vertex label as the edge label. For that, what is that we are going to do is we count the number of labels in it. That there are 15. So we take 15 new vertices and label it with these numbers 12, 13, 15, etc. up to 35 and join with 0. So, so this is what I have done. So I've taken 15 new vertices and label it with them and join it with 0. Then what is the quality now? All these labels appear as both vertex labels as well as the edge label. These are all appearing as the edge label, both vertex label as well as the edge label. Therefore, this is settled as both as a vertex label as well as edge label. Now, if you look at what is the status is, this is what status. All this V star. Now, this exclusive vertex label, each star is exclusive edge labels. All other things are appear as both vertex label and edge label. From 0 to 41, excluding 0, all the label, excluding these two, appear as both vertex label and edge label. Now, what is that we have to do is, the strategy, the game strategy is make these labels 2, 3, 4, 5, 7, 8, 10, 11, 31, 37 as edge label and make these edge labels, exclusive edge label 14, 17, 21, 30, 32, 33, 36, 38, 39, 40 as vertex label. That is the strategy. So how do you do that? How do you do that? So we have to convert all these red color labels, edge labels, as vertex labels, all these blue color labels as the edge label. So what is the game? How we are going to play the game? So if you look at this E star, 14 being the minimum of this set, which means that 0 to 13 all must appear as the vertex label. You can observe that 0 to 13 all will appear as the vertex label. Okay. So what I'm going to do is I want to make it these two as the edge label and 14 as the vertex label. For that, I take new vertex. For that, what is that I do? First, I do simple base work. What is that? I subtract 2 from 14. So I get 12. Therefore, 12 must appear as the vertex label. Yes, 12 is appearing as the vertex label. Okay, good. Now, I take one new vertex and label it with 14 and join with 12. Okay. So in that process, what is the achievement we have made is, we have made this 14 as the vertex label in the new tree and the 2 as the edge label in the new tree. We are extending this tree by adding one edge. In the new tree, what we have obtained, we are able to induce this 14 as the vertex label and we are able to induce this 2 as the edge label. This 14 is vertex label and 2 is edge label. That is interestingly done. Okay, very good. The same strategy we can adopt again. So what we do, now we update this set B star by removing 2 and update the set E star by removing 14. So this is the updated set. Okay. Now look at this E star. Currently, this is the minimum. That means all the labels from 0 to 16 now appear as the vertex label in the newly defined current tree, updated tree, extended tree. Okay. So Then what is the strategy again we adopt? You subtract 3 from 17, we get 14. The 14 must be a vertex available in the updated tree. Okay. Take a new vertex, label it with 17 and join it with 14. Therefore, we are getting 17 as the vertex label, 3 as the edge label. So 17 as the vertex label, 3 as the edge label. Good. So in this extended tree, we get 17 as the vertex label, 3 as the edge label. So we update the set V star by removing 3 and update the set V star by removing 17. Okay, again, continue this strategy. So what is that we do? Now we want to make 21 as the vertex label and 4 as the edge label. 21 being the minimum, all the label from 0 to 21, 20 must be uptime, must be available as the vertex label. Therefore, we subtract 4 from 21, 17 we got. 17 should be available as the vertex label, vertex having the label with the label 17. Therefore, take a new vertex 21, label it, and take a new vertex, label it with 21, join it with 17. We get 21 as the vertex label and 4 as the edge label. Good. So again, so update the V star and V star. Okay. Again, follow the same strategy. Subtract 5 from 30, 25 you get. So 25 must be available in the updated tree and take a new vertex, label it with 30, join with 25. We get 30 as the vertex label and 5 is the edge label. Okay, in the extended. Update the V star and E star. Again, follow the same strategy. Subtract 7 from 32, 25. Therefore, there exists a vertex in the new updated tree with the vertex label 25. Take a new vertex, label it with 32, join with 25, and then we get 32 as the vertex label, 7 as the edge label. Update the V star, E star. Okay. Same strategy again you follow. So subtract 8 from 33, 25 is available. Therefore, take a new vertex, label it with 33, join it with 25. And now you can realize 8 as the edge value, 33 as the vertex label. Therefore, we can update the V star, E star. Then 36 is the we subtract 10 from 36, we get 26. 26 must be available as the vertex label and take a new vertex, label it with 36, join with 26. Then we can realize 36 as the vertex label and 10 as the edge label. Again, update V star and E star and subtract 11 from 38, we get 27. 27 is available as a vertex label in the new extended tree and take a new vertex, label it with 38, join with 27, and we get 11 as the edge value and 38 as the vertex label. Again, update V star and E star, subtract 31 from 39. 8 is available as the vertex label, and then take a new vertex, label it with 39, and join with 8, and then you can get 39 as the vertex label or vertex and 31 as the edge label. So update the V star, E star. Now subtract 37 from 40. 3 must be available as the vertex label. Take a new vertex, label it with 40, join with 3. We get 37 as the edge label and 40 as the vertex label. And update V star and E star empty. We have got the fantastically graceful tree, larger graceful tree containing given tree as its subtree. Right? That is the beauty of this algorithm. So methodically we have done. It's not that what tree we are taking is matter. any tree, this strategy works, right? That is the beauty of this approach. So this is published in one of the highly reputed journal called Discrete Mathematics, published elsewhere. And highly appreciated. This method is highly appreciated, and the algorithm is given. Clearly, algorithm is given. How to look at the given tree and organize and give labels. Labeling scheme is given, and then yeah, then organization of those sets, this V star, E star, X star, I, and all those things. The construction of T star, T star from T dash is explained clearly here, and it works. So okay, all that good. Okay, now how do you solve this graceful tree conjecture? What is the way we can solve it? I'm proposing a new problem to solve the tree conjecture. What is the new problem I'm proposing is this. If anyone proves that if T is a graceful tree, whether it is true that T minus V is graceful, where V is any one vertex in T. So I'm doing the reverse problem. What I've done is I've taken a tree, arbitrary tree, and I developed a super tree that is graceful tree. Now I'm asking the reverse question. Suppose you have a graceful tree, that is tree with graceful labeling strategy. Then you remove one vertex with the degree 1, then that will be again a tree. The T minus V again a tree. Whether that tree, the subtree, can you make it as graceful? What is that strategy which I have followed was from given tree, I was keep on adding edges with a label, and finally I'm arriving at graceful tree. Now I'm asking the reverse question. Suppose you start with the graceful tree with the labeling, and you pluck out the pendant edges one by one. Arbitrarily, you can pluck out any edge. I mean, reduce the size of the tree by 1. Then, with the reduced size tree, can you have a strategy of having graceful labeling? That is the question I'm asking. That is the reverse question I'm asking. What we have done is the addition we have done. I'm asking for deletion strategy. The addition, I've given the strategy. I'm asking the question for deletion. Deletion, whether it is do that. That is the inverse process. Whether do you have a method? That is a question. If anyone comes up with this, solving this one, then suppose you know the answer for this question, then what we can do is, so what I have added is I can delete, and I want with the new available technology, that new one which is not known right now. Suppose if it is known, this labeling will be slightly modified. Then after the modification, this reduced size tree will be graceful. Now right now it is not graceful. Afterwards it will be graceful. The same way, if keep on doing that, because we have added edges pendant edges one by one sequentially. Suppose we have deletion technology, deletion strategy. Then if we do that one by one, finally we arrive at the original given input with the labeling, the modified labeling. That will be graceful. Therefore, that gives a way for settling the conjecture. This is the idea. So this we are able to handle the arbitrary, but not settle the conjecture. But we are expecting some more problem to be solved. Once that is solved, then we can settle the conjecture through our technique also. That is what we have contributed towards settling the conjecture of this the notorious conjecture. So Okay. With this, I will stop my talk. Right. If the audience, if you have any question, please ask. If you have a question from the audience side, please ask.
Thank you, sir.
Thank you.
Actually, no questions from the audience.
Okay, good.
Okay, thank you, sir. Thank you very much for the clear presentation, sir, and the clear explanation.
Thank you very
It's my
much.
great propose. Okay. It's my great pleasure to propose a vote of thanks for today's webinar. First, I would like to thank our Secretary, Sri Ashok Kumar Muntraji, our beloved Principal, Dr. Santosh Babu, for their valuable guidance and support. My sincere gratitude to the resource person of today's webinar, Dr. G. Sethuraman, Professor, Department of Mathematics, CEG Campus, Anna University, Chennai, for sharing his knowledge on the topic, Graceful Tree Conjecture. Really, it is an interesting session, sir. We came to know about the structural characterization of the graceful graph and some open conjecture, binomial trees, and then graceful tree, etc. Thank you very much, sir.
Thank you. Thank you very much for listening peacefully and
Thank you, sir.
patiently. Thank you.
At the outset, I like to thank.
Yeah, I
Yes,
would
sir.
be very much interested to interact with students or faculty. Someone is interested. Maybe later on they can contact me if they have any query.
Sure, sir.
Right.
Thank you, sir. At the outset, I like to thank the Professor Venkatramanan, Conveyor and Head, PG and Research Department of Mathematics, DG Vaishnav College, for his active involvement, encouragement, and guidance. I extend my sincere thanks to the organizer, Dr. Abhirami, all the faculties of the Department of Mathematics for their support. My special thanks to the technical team for making this event possible. Thank you all. Feedback link is posted in the chat box. Participants can fill the form and submit. Our department is conducting C4 classes for CSIR aspirants on all Saturdays and Sundays. I request the participants to subscribe our channel and join the Telegram link for further updates. Thank you all once again. Thank you. Thank you, sir.
Thank you. Thank you for the opportunity. Thank you.
Thank you, sir.
Right. I can leave, right? Yeah.
Sir, we have one question, sir, in the chat box.
Please. Yeah.
Yes, sir, we have one question. Is the vertex can be labeled from 1?
Yeah, it is possible. Like, it's not a problem. So we just translation. Okay, we can start from 1 and m plus 1 instead of m. We can go like that. It is not a problem. We can
Okay,
start from 1. Right. It is not a problem.
okay, sir. Thank you, sir.
Right. Thank you. Right. Thank you. Thank you very much. Right. I leave the studio. Right.
Okay, sir. Thank you, sir.